in section 1.3, the next example we're going to look at is example 3, which is graphing a piecewise defined function. These kinds of functions will play a very, very important role in chapter 2 once we begin our discussion on limits. The way a piecewise defined function is created, kind of as the name implies, is it has different pieces over different subsets of its domain. For example, the function h of x is equal to 1 minus x when x is less than 1. However, for values of x that are greater than or equal to 1, h of x has the expression the square root of x minus 1. One of the first things we would do before even trying to graph these things is to get comfortable with how to do a function evaluation. For instance, if I wanted to find the value, let's say h of 0, in order to see which piece that value x equals to 0 will get plugged into, you have to see which of these test conditions the x value of the input would satisfy. Here, because it is true that 0 is less than 1, then it's going to get plugged into the 1 minus x. So this would be 1 minus 0, which would be equal to 1. A value of x will only ever satisfy one of these test conditions at a time. It will never be plugged into more than one piece at a time for the function. One of the ways that I kind of like to describe in terms of how to graph these things is to just graph each of the functions, the pieces in their entirety, and then erase them for what portion of the subdomain you don't need it on. For example, if we look at 1 minus x, it might be more helpful for some of you to rewrite it as negative x plus 1. We would recognize this as the graph of a straight line whose y-intercept is 1 and whose slope is negative 1. So I could start up here at 1 on the y-axis. If I go over 1, down 1, that would give me another point in the line. I could go over 1, down 1 again. But this is what that line would look like. So this would be the complete graph of 1 minus x. However, we know that that's only going to be valid for x's that are less than 1, namely everything over here to the left. So this portion I'm just going to kind of go ahead and erase. Furthermore, one of the other things that we want to do here is we notice that technically we're not allowed to plug x equals to 1 into this part because it's for x's that are strictly less than 1. But if you wanted to kind of get a sense of where it stops, you can plug it in just to kind of see where this thing would finish. And it's going to be equal to 0. So here at x equals to 1, we have kind of an open circle, and that's where the first piece stops. The second piece is the graph of the square root of x minus 1. We're about to cover this part in a little bit more depth, but you would hopefully recognize this as being the graph of the square root function that is going to be horizontally shifted 1 unit to the right. So starting at 0, it's going to fill this part in. The graph of the square root function would look something like this. And this would be our complete graph for h of x. It's a piecewise defined function. For x's that are less than 1, the graph of f looks like a straight line, the straight line 1 minus x. And for values of x that are greater than 1, greater than or equal to 1 that is, it looks like the graph of the square root of x minus 1. So what do we mean when we say the graph of a function? Well, the graph of a function corresponds to the following set of ordered pairs. They're the ordered pairs x, comma f of x, where x is in the domain of f, and f of x is its corresponding output. And the different graphs and different equations and functions that we have will produce different shapes and kind of different graphs overall. If I pick any point, for example, that's on this black curve, the graph of y equals to f of x, that ordered pair, x, comma f of x, would satisfy the equation y equals to f of x. So in general, you plug x in. So think of the x value of the domain as on the x-axis. The range, the collection of outputs, are on the y-axis. Not every graph will be that of a function. If you have a graph, and if you want to determine whether that graph defines a function or not, we can use the visual tool, which is called the vertical line test. You will also sometimes hear me just kind of abbreviate it. I'll just call it the VLT. What the vertical line test says is the following. If each vertical line intersects the graph in at most one point, then the graph is that of a function. In other words, it does define y as a function of x. That is, if every vertical line intersects the graph in at most one point. Conversely, if there exists any vertical line, so if you can find even a single vertical line that has more than one point of intersection with the graph, then that graph will not be a function. So y is not a function of x. There is a huge laundry list of functions that you should have kind of memorized all together. Hopefully these are graphs that you're kind of familiar with. The constant function and identity function are just kind of two subcases of general lines. So hopefully everybody knows how to graph y equals mx plus b, or more generally now, using function notation, f of x equals mx plus b. If the line has no slope, then it's a horizontal line, and it would look like this. One particular function that's of interest is the linear function with a slope of 1 and a y-intercept of 0. This is sometimes referred to as the identity function. The identity function has the unique property that whatever you plug in is exactly what you would get out. The expression for this is f of x equals x. So if you plug 1 in, you get 1 out. If you plug 2 in, you get 2 out, etc. The next common function that hopefully everybody knows is the absolute value function. The absolute value function, we'll spend quite a bit of time considerably on this, but at its heart, absolute value is actually a piecewise defined function. Most people just know, or most students just kind of know it as the function that makes everything on the inside positive as a real number. But the way that it does so is that the absolute value of x is defined as x when x is greater than or equal to 0. So for example, what is the absolute value of 7? Well, the absolute value of 7 we know is just 7, simply because the thing on the inside was positive or 0. But what happens if the thing on the inside is negative? Well, if x is less than 0, meaning if x is negative, then you return the opposite of x. Okay? So for example, the absolute value of negative 3 would be equal to the opposite of negative 3, and that's how it turns it into a positive 3. So absolute value is piecewise defined. It's x when x is greater than or equal to 0, and it's negative x when x is less than 0. And that's exactly kind of what we see. When x is less than 0, to the left, it looks like a line with a y-intercept of 0 and a slope of negative 1. That's this part right here. And when x is greater than or equal to 0, it looks like the graph of x, which should have a y-intercept of 0 and a slope of a positive 1. And altogether, cumulatively, it kind of makes that V classical shape that you're used to seeing from absolute value. You should also note the domains and the ranges of these functions. When you're looking for the domain of the function, if you're looking at it from its graph, you're looking on the x-axis, how far left and how far right the graph extends without any breaks or gaps or missing points, that is the domain. Because of these arrows, this graph will go all the way to the left. It goes all the way to the right. And so that's the domain negative infinity to positive infinity. For the range of this function, Now, when you're talking about the range, you're looking at the y values or the outputs. So now we're going to be on the y-axis. The lowest point is the actual vertex here, which is at 0 on the y-axis. Because of these arrows, it's going to go up and up and up forever. So on the y-axis, the range of this function is from 0 to infinity. If you kind of go back to outputs, these would be the kind of outputs you could get as a result of plugging something into the absolute value. We know that the smallest the absolute value could ever be of something would be 0, precisely when we plug in 0, and then beyond that, it's always going to be some positive value. So that's why you see the positive y values going up for the range on this one. We should also know what the graphs of some basic polynomials look like. The graph of f of x equals to x squared, this is our basic quadratic graph. And in many ways, this is also kind of indicative of what x to the n for n even looks like. So if you wanted to look at the graph of, let's say, x to the 4th, or x to the 6th, or even x to the 2020th power for that matter, the graphs are all going to have more or less the same shape. The only way in which the exponent is going to affect it is that the higher the exponent, kind of the steeper it will rise, but it will still kind of maintain that same overall U shape. So the graph in red would be like x squared. This one could have been, let's say, maybe like the graph of x to the 6th. So definitely want to know what the graph of an even-powered polynomial looks like. Has domain all real numbers. It too would have a range from 0 to infinity on the y-axis. The square root of x has a graph that looks like this. This overall shape, so first of all, the domain of this is from 0 to infinity on the x-axis, and the range is also going to be from 0 to infinity on the y-axis. This particular graph, this shape, is also indicative of the nth root of x, where n is even. So 4th roots, 6th roots, 8th roots, etc. all have a graph that kind of looks like this overall shape. Increasing the index just kind of makes it rise a little more slowly. So if this would be like the square root of x, this graph below it could be something like, I don't know, the fourth root of x. But they'd have more or less the same shape, just the scale would be a little bit different. X cubed is in many ways the classic graph of a polynomial of odd degree of 3 higher. It has domain all real numbers from negative infinity to positive infinity. Same thing too with the range, it goes all the way down and all the way up on the y-axis in terms of outputs. So its range is all real numbers. This classical graph is very similar to the graph of x to the n for n odd, and also greater than 1. If n is 1, then that's just a straight line. But things like x to the 5th, x to the 7th, etc. would look very much like what the graph of x cubed looks like. Similarly, if you wanted to look at the graph of an odd root, for instance the cube root, it has a graph that looks like this. Has domain all real numbers. Also has range all real numbers. It just rises and falls very, very, very slowly, but it will tend to negative infinity on the left side, and it will tend towards positive infinity on the right hand side. So this is the graph of x, the cube root of x. So these are just some of the elementary functions graphs you should know. We also should remember some basic graphs from trigonometry. In particular, everybody should know what the graph of the sine of theta looks like. The cosine of theta as well is a graph you should know. And then the other one that we'll focus on quite a bit will be the tangent of theta. It would be nice if you knew the graphs of secant, cosecant, and cotangent. We won't use them quite as much throughout our class, but they will certainly pop up from time to time. But certainly these are very, very popular. Sine, cosine, and tangent, so make sure you know those graphs. one of the most basic rational functions, which is just the quotient of two polynomials, y equals to 1 over x. It's the first function example that we've seen in this section that has an asymptote. The denominator is undefined. Excuse me, the division is undefined when x equals to 0. So 0 would not be in the domain of this function. And then what you would see is that the vertical line x equals to 0 would be a vertical asymptote for this rational function. We'll come back to these later. We'll spend an entire section later on in the class specifically graphing rational functions, but certainly one of the easiest ones is 1 over x. It's also sometimes referred to as the reciprocal function, so you should know its graph. We also want to know the graphs of basic exponentials and logarithmic graphs. Again, they kind of come in two different flavors depending upon the magnitude of the base. If the base is bigger than 1, then the exponential function looks like this. It approaches 0 as x approaches negative infinity, and as x approaches positive infinity, the graph approaches positive infinity. It also has the y-intercept of 0, 1, and that's specifically because any positive base raised to the 0 power gives the result 1. So this is the first type of exponential graph. This would also be indicative of things like 2 to the x, 3 to the x, and the ever popular exponential function e to the x, which has a base of 2.718, etc. If the base is between 0 and 1, so things like 1/2 to the x, or let's say like 0.10x, then it kind of opens in the opposite direction. As x approaches negative infinity, the function would approach positive infinity, and as x approaches positive infinity, the graph would approach 0. So make sure you know what the graph of the basic types of exponentials look like. And then similarly, here's what the graphs of logarithms look like. If your base is bigger than 1, it looks like this. It has x equals to 0 as a vertical asymptote. It has an x-intercept of 1, 0. And if the base is between 0 and 1, then it would look like this. This graph here, by the way, so if the base is bigger than 1, this would include things like log base 2 of x and the ever popular natural log, which is the ln of x.